Welcome back to Chapter 9, Nuclear Radiation. We are in Section 4 of Chapter 9, and we're going to look at the half-life of radioisotopes. The half-life of radioisotope is the time for the radiation level to decrease or to decay to 1/2 of the original value. And so these times can vary tremendously. If we look at a chart of some naturally occurring versus medical radioisotopes, you will see that, say, carbon-14 has a half-life of 5,730 years. So this is a really long time. So it's basically the time that it's going to take for half of a sample to decay over that many years. If you look at some of the radioisotopes used more for medical purposes, iodine-131 used for thyroid, for help with hypothyroidism, it has a half-life of 8 days. So a tremendous amount, tremendously less than that of carbon-14. Technetium also, this is used, I think I mentioned another video for stress tests. It has a half-life of 6 hours. Okay, but then it talks about what radiation is being emitted. So you have gamma, which we know is the most penetrating, beta, alpha, gamma, all of the things that we've seen in our radioactive equations. But one of the big problems with this is that because the half-life of some of these radioactive isotopes take so long to decay, we run out of places that we can store and dispose of radioactive material. So it's very, very scary in the sense of there's only so many places that you can dump radioactive material and not harm, be harmful to the people that live in the area or the surroundings. And because they have such a long half-life, some of them that take hundreds, thousands of years to decay, this poses a major problem in trying to dispose of these materials. If we're going to calculate a half-life, we're just going to state what we're given and what we need. We're going to write a plan of how we're going to calculate the half-life, and then we're going to have to convert it. Okay? So if we have a radioactive isotope, strontium-90, has a half-life of 38.1 years. If we have a sample that contains 36 milligrams, then how many milligrams will remain after 152 years? So basically, we're going to state what we're given. We have 36 milligrams, 152 years, and a half-life of 38.1 years. Okay, so we're going to need to find milligrams remaining. So we need to write a plan. We've got 152.4 years, and we need to look at how many half-lives is this. Okay, and then once we do that, then we can come up with the amount that we will have left. Okay, so the first thing we want to see is that our half-life is 38.1. So that's 1/2 life. Okay, so if we think about in 152.4 years, how many half-lives is this going to be? So I need to go back here for a second. Looks like it doesn't say. Okay, but if we take, so the first thing that I would do here is, let me get my pen. Okay. So we want to know how much is going to be left after 152 years. How many milligrams? So we have 38.1 years, and so we're basically going to have to divide 152.4. That's how long we want to know how much is going to be left after that long, and we get 4 half-lives. Okay, so I think we have a little typo here. 152.4 years. So 152.4 divided by 38.1 is going to give us 4 half-lives. So we're going to half our original amount 4 times. Okay, so if we take 36 and we cut it in half, so we half it, so take 36 divided by 2, you get 18. That was 1 half-life. Okay, then we're going to just keep doing this as a running total in your calculator. So that's 1 half-life, but we have to go 4 half-lives. So we would take 18, divide it by 2, and we get 9. So that was our second half-life. If we divide 9 by 2, we get 4.5. So each time we're dividing by 2, so divide by 2. So we've gone 3 times, so now we have to divide 1 more time. So we divide by 2 again, and we get 2.25 or 2.3 milligrams. So the main thing is you have to come up with the number of half-lives. So here we have 4 based upon what we know our half-life is and how many years total we want to be looking at. And then you just take your original sample and you can divide it 4 times by 2. Okay. The half-life of iodine 123 is 13 hours. How much of a 64 milligram is our sample, of I-123 is left after 26 hours. Okay, so it has a half-life of 13. And we want to know how much is left after 26 hours. So 13 into 26 is 2. So that's going to be 2 half-lives. 2 half-lives. Okay. So we're going to take our 64 milligram sample. We're going to divide by 2. This will be our first half-life. 64 divided by 2 is 32. And then if we divide by 2 again, for our second half-life, we got 2 half-lives, so we divide through by 2 twice. So 32 divided by 2 is 16 milligrams. So our answer would be B, 16 milligrams. We can also use an equation to find the half-life, and you may find this easier, or you may like doing it the other way that your book shows in the 2 examples that we've just gone through. So it's really up to you. Some of you may like equations better, whatever you may think. But we can find the grams, or the mass final. So MF, F stands for final, by taking the mass of our initial sample, times it by 0.5, so that's for the half, and then we use to the power of n. Okay, this is to the power of, and n is equal to the number of half-lives. Okay, so we're going to do a problem that we do it this way. So we have cobalt 60 has a half-life of 5.25 years. If 2.65 grams decays, how much of the initial sample is present after 3 half-lives? Okay, that's going to be one of ours. Okay, we're going to do 2 problems actually from this, but so we're basically trying to find MF. So we would plug in our mass initial, which is 2.65 grams, times 0.5, and then our number of half-lives, it's giving it to you. We're not having to find it after 3 half-lives. So it gives it to you. So all we have to do is say, put a 3 there. And if you do the math, be sure you do to the power, to the 3rd power. Okay, so it's going to be 0.331 grams cobalt-60 that is left after 3 half-lives. Okay? What if we were asked after 21 years? This would be part B, part A. Alright, this time we're not given the half-life, but we can go ahead and set it up the same. Mass final equals 2.65 grams. That's what we're given. You have to be given a mass of your initial sample times 0.5 to the power of n. And this is where we do not know n yet. We've got to solve for it. Okay, so if we take 21 years, that's how long the sample is going to be decaying. And we go up here and we see that we have a half-life of 5.25. Then this is just like what we were doing earlier. This was that first step, or big step that we had to do, is find the half-life. So we have 4 half-lives. So now we would plug in a 4. Whoops. And we would get 0.166 grams cobalt-60. Okay, so you could just be given the half-life, even with the problems that we have done previously. If you're just given the half-life, then you just have to sample that many times. So either way you like to look at it. Some people are more equation-minded. Some just want to say, once they get it, they can just keep dividing by 2 once they know the half-life. Okay, if you have to find the half-life, basically you take the total time that the radioactive species is decaying, and you divide it by its half-life to get the total number of half-lives. And then you can place it here, or you can do it the way that we did on the previous slides. Thank you, and this concludes the videos for nuclear